Hello and welcome to lecture 4, Wave Properties of Light, first class. This is a lecture on online class with a course code of EEE 4233. The course name is Optoelectronics. At the end of this class, we will be able to learn what is the wave properties of light, working principle of Gaussian beam, importance of refractive index, and finally the principle of group velocity and group index. This is the chapter 1 of Kasav's book, Wave Nature of Light, and this is a figure of Sir William Begg. Now, what is a light? Light is basically an electromagnetic wave, a wave that is traveling wave that has the time variance of electron and magnetic field at that perpendicular to each other at the direction of propagation is z. Here is a mathematical explanation of electromagnetic wave where Ex is the electric field along x at position z at time t, k is the propagation constant twice pi by lambda, lambda is the wavelength, omega is the angular frequency where omega equals to twice pi mu where mu is the frequency, E naught is the amplitude of the wave, phi naught is the phase constant at t equals to 0 and z equals to 0. Ex may or may not be necessarily 0 depending upon the choice of origin. And finally the omega t minus k z plus phi naught, which is equals to phi, which is the phase of the wave. This is a monochromatic plane wave of infinite extent traveling in the positive z direction. What is a wavefront? A surface over which the phase of a wave is constant is referred as wavefront. A wavefront of a plane wave in a plane is perpendicular to the direction of the propagation. The interaction of a light wave with the non-conducting medium where conductivity is 0 uses the electric field component Ex rather than By. Optical field refers to the electric field Ex. Here we are seeing a wavefront where we can see that E and B have a constant phase in the xy plane, a wavefront, and Ex becomes E naught e to the power sine omega t minus kz. A plane EM wave traveling around z has the same Ex or By at any point in a given xy plane. All electric field vectors is a given xy plane are therefore in phase. The xy plane are of infinite extent in the x and y direction. Phase velocity. The time and the space evaluation of a given phase phi, for example, that corresponds to the maximum field is described by phi equals to omega t minus kz plus phi naught equals to constant. This is the maximum field that is to be described. During a simple time interval of delta t, this constant phase and hence the maximum field moves a distance delta z. The phase velocity of the wave is therefore delta z divided by delta t. The phase velocity v can be said as mu naught or omega by k equals to mu into lambda. Now we will discuss a new concept which is known as Gaussian beam. The radiation emitted from a laser can be approximated by a Gaussian beam. Gaussian beam approximations are widely used in a photonics crystal saver or photonic electronics. Here is a figure. We can see that wavefronts of a Gaussian light beam where there are some wavefronts and z is the beam axis. Beam west is 0, which is twice w naught. Let's explain how it works. Now the intensity across the beam follows a Gaussian distribution. Here we can see the intensity I, which is a function of r and z, equals to equation of twice p by pi omega square into exponential of twice r square by omega square, where theta equals to w by z, which is z, which is lambda divided by pi omega naught. Twice theta is the far field divergence. If we explain simply, we can see that if a laser light goes from its point, it starts to divergence. The Gaussian beam mainly shows how much it diverges. Here we can see the intensity of the power and the Gaussian power also. So twice theta equals to far field divergence. In optics and especially in laser science, the Rayleigh length or Rayleigh range is the distance along the propagation direction of a beam from the west to the place where the area of the cross section is doubled. A related parameter for the confocal parameter b, which is the twice of Rayleigh length, where z naught equals to pi omega naught square divided by lambda, where z naught is the Rayleigh length. Now, this is a special spherical mirror where we can see that Gaussian beam works. However, twice W is the equation of Rayleigh length and Rayleigh range is W0. These two equations are very important to solve a mathematical problem related to the Gaussian beam. There are some difference or there are some changes between the ideal Gaussian beam and the real Gaussian beam, where m square for a Gaussian beam is equals to 1, whereas in real beam m square, which is greater than 1. M square is known as quality factor and it is given as equation here. We can see this is an equation of m square and this is an equation that is modified equation of Rayleigh length due to the real beam of m square. So if we use a real beam, we would get an equation of like this, which represents m squared, the quality factor. So this equation shows that this is a for real Gaussian beam. There is a correction in page 10 of the textbook. The equation 1.11.1 omega should be omega r as above, and omega r naught should be the squared in the parentheses. So this is the exact correct equation. So just make a correction to the textbook's equation. So, Gaussian beam in an optical cavity. The two spherical mirror reflects wave to and from each other. The optical cavity contains a Gaussian beam. This particular optical cavity is symmetric and confocal. The two focal points coincides at F point. Now we see an example of a Rayleigh length problem, a diverging laser beam. This is an example from optoelectronics Kasab's book. So if you want, you can go through the book also. So consider a helium neon laser beam at 633 nanometer with a spot size of 1 millimeter. Assuming a Gaussian beam, what is the divergence of the beam? Number 1 point. Another one is what is the Rayleigh length range and the beam's width at 25 meter. So we know the equation of the Rayleigh length twice theta, which is known as far field divergence. So we get equation from there and put all these parameters, we will get an equation result at radian. Then if we convert in degree, so we get 0.046 degree twice theta. And so the Rayleigh length z naught, the range is 1.24 meter. The beam width at a distance of 25 meter, we would get twice Rayleigh length range is 20 millimeters. So we see that the higher the distance, the Rayleigh lengths are much more lesser. It is very much physically acceptable. Refractive index. When an EM wave is traveling in a dielectric medium, the oscillation or oscillating electric field polarizes the molecules of the medium at a frequency of the wave. So the stronger is the interaction between the field and the dipole, the slower the propagation of the wave. Here is a table of low frequency, relative permittivity, and the refractive index of that. We can see that silicon, diamond, gallium arsenide, silicon dioxide, water, they have different kind of low frequency relative permittivity and also the refractive indexes. Phase velocity and epsilon r. The relative permittivity epsilon r measures the ease with which the medium becomes polarized, and hence it indicates the extent of interaction between the field and the induced dipoles. For an EM wave traveling in a non-magnetic dielectric medium of a relative permittivity of epsilon r, the phase velocity mu becomes 1 by root over epsilon r, epsilon naught, omega naught, where epsilon r is the relative permittivity, mu naught and epsilon naught are the relative equations parameter. So here are some equations for refractive index n, where v equals to 1 by root over epsilon r epsilon naught omega mu naught, and refractive index n as defined as c by v equals to root over of epsilon r. Okay, optical frequencies. Typical frequencies that are involved in optoelectronic devices are in the infrared, including far infrared, visible, ultraviolet, and we generally refer these to frequencies as optical frequencies. Somewhat arbitrary range is about 10 to the power 12 Hz to 10 to the power 16 Hz. So refractive index and propagation constant n equals to k by k naught, where k naught is a free space propagation constant, which is a wave vector, and k is the propagation constant in that medium, where k naught equals to twice pi by lambda naught. Lambda naught is a free space wavelength. In non-crystalline materials such as glass and liquids, the material structure is the same in all directions, and n does not depend upon the direction. The refractive index is this then called as isotropic. So we can see that refractive index and wavelength relation, it's a customary drop to the subscript 0 on k and lambda, where k medium equals to n into k, where lambda medium is lambda divided by n. These two equations will be needed for mathematical problem solution later on. So refractive index and isotropy. Crystals in general have non-isotropic or anisotropic properties. Typically, non-crystalline solids such as glass, liquids, cubic crystals are optically isotropic. They possess only one refractive index for all directions. Okay, let's come to the last topic of our lecture. It is the group velocity and the group index. So if we can see that there are no perfect monochromatic waves, we have to consider the wave in such a group where they are slightly differ each other in wavelength travel along the z direction. So when two perfectly harmonic waves of frequency omega minus del omega and omega plus del omega wave vectors with k minus del k and k plus del k interfere, they generate a wave packet which contains an oscillating field at the mean frequency omega that is an amplitude modulated by a slow varying field of frequency delta omega. The maximum amplitude moves with the wave vector delta k, and thus with a group velocity that is given as Vg equals to del dk divided by d omega. So it's a pictorial diagram. We can see that omega plus del omega and omega minus del omega, when they're combined, they makes an amplitude modulation with del omega frequency and moving towards del k direction. It's a periodic wave packet. So the overall velocity of that combined wave is known as group velocity. The two slightly different wavelength waves traveling in the same direction result in a wave packet that has an amplitude variation that travels at a group velocity. Here we can see another picture where the group velocity or a single wave packet Vg is given with a mathematical derivation or mathematical equation. Okay, if we come to the mathematical derivation of group velocity, we consider two sinusoidal waves that are close in frequency, that is a frequency of omega minus del omega and omega plus del omega. Their wave vectors will be k minus del k and k plus del k. The resultant wave would be then E naught cos omega minus del omega t plus E naught cos omega plus del omega t. By using trigonometric identity, we can see that twice E naught omega cos A and cos B. So this equation represents a sinusoidal wave of frequency omega. This is amplitude modulated by a very slow varying sinusoidal of frequency del omega. This system of wave, for example the modulation, travels along z at a speed determined by the modulating term cos omega t. This is the modulating term. If you can see from here, this is the modulating term cos omega. The maximum in the field occurs when this field becomes constant. So from there we can get this equation or Vg equation. So this is the derivation of the group velocity of the wave, because it determines the speed of the propagation of the maximum electric field along z. So the derivation of the group velocity is important for the exam. So if there is a question how group velocity can be derived, you have to write this derivation equation from here. So the group velocity therefore defines the speed with which the energy and information are propagated, where omega equals to twice pi c by lambda naught and k is twice pi n lambda naught, where lambda naught is the free space wavelength. If we differentiate it, we would get the group velocity final equation c divided by n minus lambda naught d lambda by d n naught. This is the group velocity equation for our final derivation of the group velocity. Now there is a relation or correlation between group velocity and group index, where n, which is a function of lambda, or a function of wavelength, the group velocity Vg in a medium can be given like this equation. Thus, it can be written as Vg medium C by Ng, where Ng is the group indexes. So Ng equals to n minus lambda d lambda by dn is known as group index of the medium. In general, for many materials, for the refractive index n, and hence the group index Ng depends upon the wavelength of the light. Such materials are called as dispersive. So there is a dispersive relation becomes the group index of the medium. So where the many materials refractive index n and the group index Ng lightly depends upon the wavelength. So let's see a mathematical problem between the group velocity and phase velocity. Consider a light wave traveling in a pure silicon dioxide glass medium. If the wavelength of the light is 1 micrometer, the refractive index at that wavelength is 1.450. Find the phase velocity, group index, and group velocity. So for phase velocity, we know that C by N, we get the phase velocity. And for group index, if we see this figure at 1 micrometer, we are getting a phase group index of 1.450 or 1.463. And finally, the group velocity Vg equals to C by Eg. It becomes 2.051 10 to the power 8 meter per second. The group velocity is almost 0.9% smaller than the phase velocity. So thank you, and if you have any query about this lecture, please note down and show it in the upcoming Zoom livecast, which will be held in every Sunday from now on. So for lecture 456, we can discuss on the Zoom live class along with some suggestive question and answer round. Thank you.